Hello everyone, welcome to Tech-Lavya. Please like, share and subscribe.
Having studied the basic terminologies about alternating current or alternating voltage, then phase difference, phase angle, phasor algebra, etc. Now let us apply those concepts. So today we are going to discuss what happens when this alternating signal is applied across resistor, inductor and capacitor. Okay? Yes. So first comes when AC is applied across a resistor. Now you can see that here AC signal, AC supply is shown. It is applied across resistor R. The magnitude is specified as 10 volts. Please remember that this is RMS value. Now I would like to share with you that whatever value is denoted with AC source, that is going to be RMS value, and peak value is not specified. So whenever it is AC, you have to consider that magnitude as RMS value. Fine? Okay. Now let us go further. Now current direction is specified, but here I think you have spotted some difference. Have you? Earlier we used to assume the direction of the current like this, isn't it? But now it is a bidirectional arrow. Secondly, just below current flow, again a bidirectional arrow is specified. Why? Why? Come on, I want the answer. Yes, because AC is a bidirectional signal. Earlier we were dealing with DC. So DC is a unidirectional signal. It flows only in one direction, right? It flows from positive to negative. But alternating signal switches between positive and negative continuously, or it changes its state alternatively. Fine, that is why the name is alternating current, isn't it? Yes. So now we will not be specifying the current in one direction. Okay, fine. That was just a basic concept. Okay. Now, any alternating signal can be given as Vm sine omega t. So the voltage across resistor is again given by Vr is equal to, Vr signifies the voltage across resistor. Subscript, whether it is R, L or C, specifies across which component we are measuring the voltage. Fine. So if it is Vr, it is going to be voltage across resistor. If it is VL, then it is voltage across inductor and so on. Fine. Now, how do we calculate the current? Now, across resistors, simple Ohm's law can be applied. Now, this law, Ohm's law, cannot be applied across or through inductor and capacitor. We'll come to that later. Fine. So, across resistance, blindly we can apply Ohm's law. So, what does Ohm's law tell us? It says that current is equal to voltage upon R, resistor. So, current I is equal to V upon R. Since we are talking about the current through resistor, it is going to be IR is equal to VR by R. Fine. So we will put the value of VR. So we have V max sine omega t. Okay. Now what is V max upon R? It is I max, right? Maximum current. So we got that IR is equal to I max sine omega t. Now this is very important. Now just compare these two signals, okay, VR and IR. Now VR and IR is okay, that is voltage and it is current, fine. V max, I max, yes, it is the maximum voltage, maximum current, so we find the similarity. Plus we have in VR we have sine omega t, and here also we have sine omega t. What does that mean? It means that the voltage and current are in phase. Okay, they are in phase. This is very important. So when I write VR, I'll just put the value. Okay, so instead of V max, I will write I max into R and I get sine omega mt. Now see, this is the phasor diagram. Now since in current equation, we divide the voltage by a resistor, and obviously resistor is going to be a non-zero value. So we always assume that current would be lesser as compared to the voltage, right? So it is going to be less than, the current is going to be less than the voltage. Okay, so the solid black line is the voltage and dashed red line is the current. Now just pay attention that where are the maximum points, where are the 0 points, positive maximum, negative maximum, everything is same. Earlier also we have studied that in this case, suppose we get the waveform like this, we say that both the quantities are in phase. Fine. So this is a very important conclusion, that the voltage and current across a resistor are going to be in phase. Fine. Okay. Now let us see what happens across inductor. So what we have done is we have connected same AC voltage across an inductor. An inductor, you know, it is a component which converts electrical energy into magnetic energy. So whenever we apply some current, it converts it into flux and magnetic field is produced. Isn't it? Yes. So inductance is specified as L and you have phi, which is flux. And sorry, the reactance of inductor, that is called inductive reactance, is specified by XL. Reactance is specified by X and L is inductive reactance, and it is given by 2 pi FL. And what is 2 pi F? It is omega, that is angular frequency. So XL can be either written as 2 pi FL or it can be written as omega L. Fine. Okay. So we will start with Vt is equal to V max sine omega t. Fine. But we know that due to Faraday's law of electromagnetic induction, because this is AC, so even if we do not move the conductor, EMF is induced because continuously the magnitude is changing. So rate of change of flux will be there. Fine. It means EMF is induced, and that EMF due to Lenz's law will oppose the cause. So this EMF induced will be same as V but will be in the opposite direction. Okay, fine. So how do we express the voltage across inductor? The voltage across inductor is given by V is equal to L di by dt. We have studied this equation in our earlier classes, isn't it? Okay. So the value of V is put in this equation, Vm sine omega, V max or Vm, whatever. I have taken it to be Vm. Okay, sine omega t, and again right hand side is the same. Fine. So what is the next step? Next step is cross multiplication. Fine. And we have converted this equation in terms of di, because actually we want current. Because we have the voltage equation, we want to get the equation of current. So I want I. In order to get I have converted, just wait. Say I have converted this equation in terms of I. So I got di. So di is equal to, that is written. Okay. And what will I do in order to get I? If I have di, I have to integrate the equation, then only I will get I. So what I'll do is I'll integrate the equation. Okay, but then it has to be applied on both the sides. So after integration, Vm and L, they are constant, right? So my equation will be, I shall write that. Okay, so I'll have di is equal to integration Vm upon L sine omega t dt. This is the equation. Fine. So Vm, yes, so Vm upon L is constant, so we will take it outside the integration sign and we get integration sine omega t dt. So what is the integration of sine omega t? It is minus cos omega t. And again I have told you earlier, now here we do not have t, we have omega t, right? So if I am integrating sine omega t with respect to with respect to dt, then it will be minus cos omega t divided by, I have to differentiate this. So it will be d by dt omega t. Fine. So the output will be minus cos omega t upon what will be integration of omega t? It will be omega. Fine. So this omega comes outside the bracket. Okay, we have done such kind of calculation. So I have written these steps directly. However, I am showing it to you how these values have come. Fine. Okay. Now, what exactly is minus cos omega t? So again in trigonometry we have studied that cos theta is equal to sin 90 plus theta, and sin 90 minus theta is, so we have converted this minus cos omega t into sin omega t minus 90 degree. So instead of 90 I have written here pi by 2. Okay, since I have minus cos omega t, if it was plus cos omega t, then my equation would have been sin omega t plus pi by 2. Since it is minus cos omega t, I got the equation to be sin omega t omega. See, it is like this. Yes, it is something like this. Fine. So it is sin omega t minus pi by 2. Okay. Yes. So this is my equation. Now, where did this Im come from? Because Vm upon omega L is nothing but Im. We know this equation because omega L is nothing but XL. Isn't it? Yes. So, I'll write that Vm is equal to Im into XL. Similarly, Im is equal to Vm upon XL. Likewise, I can use these laws. Fine. Okay. Yes. So first let me erase everything. Fine. So this is the phase diagram. Now see, current has sin omega t minus pi by 2. So what does that mean? It means that current lags inductor by 90 degree. Current lags the voltage by 90 degree. So x-axis is IL and y-axis is VL. Okay, you can very well see that current lags voltage by 90 degree. Now I can conclude this from comparing these two equations also. How? Because the first equation, voltage equation, has sin omega t and the second equation has omega t minus pi by 2. So I can conclude it here itself, right? Yes. And this is how the waveform actually looks like. So you can see that the voltage starts at this point, whereas the current is starting at this point. And this is nothing but pi by 2 because sine wave attains maximum value at pi by 2. So when sine wave, the voltage attains maximum value, at that time my current is starting. Getting it? So I can conclude that current is lagging in case of inductor. Please remember these concepts because we are going to apply these concepts later. Fine, okay, resistor is over, inductor is over. Let us talk about capacitor now. So this is how I have connected the AC voltage across a capacitor. So again, reactance of the capacitor. There it was XL is equal to 2 pi FL. We have already discussed these terminologies. Okay, you can refer to those points. Now, XC is 1 upon 2 pi FC and 2 pi F is nothing but omega. So XC can be written as 1 upon omega C. Fine. And we also know that Q is equal to CV. Correct? That is Q is the charge. And the current across capacitor is, or for that matter, what is current? Rate of change of charge, isn't it? Flow of electron is rate of change of charge. So I can say that I is equal to dq by dt. Okay, so I'll apply it. I'll write the value of v, because we have already written v is equal to vm sin omega t. I did not write that equation because it is anyways coming. So d by dt, and what is q? Q is cv, so c into v, and v is vm sin omega t. Fine. What I'll do is, for your better understanding, I'll write here I comes out to be d by dt q, so that comes out to be cv. So this becomes d by dt c into vm sin omega t. This is how it came. Okay, yes. So again we know how to go ahead. So Vm is constant, C is constant. So we are going to differentiate sin omega t, right? Now I'll write it here. So I have d by dt sin omega t. I have taken CVM outside the differentiation because they are constant. So what is the differentiation of sin theta? It is cos theta. So it is cos omega t, correct? Multiplied by, again, because this is not theta, this is not t, this is omega t, correct? So it gets multiplied by omega. Fine. So d by dt of sin omega t comes out to be omega times cos omega t. So this is the equation which we got. Okay. So what is cos theta? Sin 90 plus theta. So we got I is equal to omega c Vm sin omega t plus pi by 2. Fine, plus pi by 2. Please pay attention here. In case of inductor, it was minus pi by 2. In case of capacitor, it is plus pi by 2. I think you can arrive at the conclusion, right? Yes, very good. So what exactly is Vm omega c? It is nothing but Im. Now how? How? Again, I'll do some rough work here. I have Vm omega c. Now what is omega c? 1 by xc, isn't it? Yes. So what is voltage upon reactance? It is current. So this is how we replaced Vm omega c by Im. So here again it is clear that what I asked you to arrive at a conclusion after looking at this equation. So what is your conclusion? I want you to repeat with me that the current in case of capacitor leads the voltage by 90 degree. Yes, very good. So see here, the phasor diagram is shown. Now it might appear same for you, but in case of inductor, y-axis represented V and x-axis represented I, whereas in case of capacitor, x-axis represents V and y-axis represents I. Fine. So current leads the voltage by 90 degree. And how does my waveform look like? It looks like this. Now you might wonder why it is looking like this. It appears to be similar. No, it is not similar because earlier my voltage was something like this, correct? It was starting, correct? It was starting. Now this is again 0. Even in capacitor it is 0, but by then it has already completed its half cycle. Getting it? Right? So if you compare this point, capacitor current has already completed maximum value here when the voltage was 0. Right? So that is why we say that it is leading. Fine? So let us talk about AC across series RL. So what happens when you have a series combination of R and L? Individual components, okay, we have discussed it. Let us see various combinations now. So this is how it is applied, and the impedance is going to be square root R square plus XL square. Now why this? Because now we know it is going to be vector addition, isn't it? Yes, because across resistor there is no phase shift between voltage and current, but across inductance we have, isn't it? Yes. So if I want to draw a phasor, so resultant vector algebra, we have already done that. So resultant is taken to be square root r square plus xl square. Now if you want it to be represented in polar form or rectangular form, you can represent it. Okay. Now how to calculate phi? Phi is calculated by tan inverse y by x. Okay. Tan inverse y by x. So y is xl and x is r. So your phi is given as tan inverse xl by r. Now since this is a series circuit, the current is going to be same, right? Whatever current flows through the resistor, the same current flows through the inductor also. So Is actually represents series current. Fine. So it represents series current. So this series current is given as the voltage upon the impedance. Now I cannot write resistance alone because now it has impedance. Okay. Yes. Secondly, Vs by Z. So we can place the value of Z here. Now if I wish to calculate the voltage, then again I have to calculate the vector sum. Okay. Fine. So how do I go about it? Now again, this is going to be VR and this is going to be VL. Okay. So this is my resultant, which is VR square plus VL square whole under root. So this is the total voltage. Fine? Yes. So this is the phase diagram. I've already told you, right? So this is the phase diagram. Now let us see what happens when AC is applied across the combination of L and C. Now you might have got the idea by now. Correct. So Z is XL square minus XC square. I'm so sorry. Yes. XL square minus XC square. Now why do we have this minus sign here? Because we have inductor and capacitor. Fine. We do not have inductor and resistor. Yes. Now since we have capacitor also, okay, so here we have minus sign. Fine. And at resonant frequency, which is FR, is represented as 1 upon 2 pi square root LC. Now this resonance frequency, we will discuss it in detail in the coming lectures. Okay. So it is specified that at resonance frequency, XL becomes equal to XC and VL is equal to VC. And of course the series current is going to be the same, right? Now let us see what happens when AC is applied across R and C. So here you have this. So again we have everything same. Okay. Yes. So it is square root R square plus XC square. But phase is going to be minus. Okay. Now I'll tell you how this phasor diagram will look like. So this is VR and here is my VC. So this is my resultant V. Okay. Yes. Because here the current leads. In case of capacitor, the current leads but voltage lags, isn't it? So that is why I am drawing it to be in the downward direction. Okay. I hope this is clear to you. So everywhere I'll get minus sign. Okay. So see R minus JXC, then tan inverse minus XC upon R. So current is calculated by Vs upon Z. Okay. So this is the phase diagram. So we shall meet in the next class. Until then, keep studying. See you.